Hi, good morning. Today we are going to start our next session, extension fields. Okay, introduction to extension field. Now, what do you mean by an extension field? So, a field E is an extension field of a field F if F is a subfield of E. A field E is an extension field of a field F if F is a subfield of E. Then F is called subfield, E is called extension field. Okay. So if we move to example, R is an extension field of Q, C is an extension field of both R and Q. Similarly, if you consider f of x, f of x means set of a ring, okay, polynomials, okay, f of x. F of y is an extension field of f, and f of xy is an extension field of f of x, and f of y also it is an extension field of f. So here is a representation of tower of fields. R is an extension field of Q, and C is an extension field of R and C. Okay, if C is here, then that means here if we have two lines, that means this is an extension field of both R and Q. Now here actually this is not Q, this is F. Okay, F of x is an extension field of F of y is an extension field of F, and F of xy is both extension field of both F of x and F of y. Also it is an extension field of F. This figure is called tower of fields. Okay. Now we are going to one of the most important theorem, Chronicles Theorem. Okay, Chronicles Theorem. Now what is the statement of the theorem? Listen carefully. Let F be a field, okay, and F of x be a non-constant polynomial in F of x. F of x is a non-constant polynomial in F of x. Okay. Then there exists an extension field E of F, and an element alpha belongs to E such that f of alpha equal to 0. What is the statement of the theorem? Let f be a field and f of x be a non-constant polynomial in f of x. Listen here, square bracket f of x. Then there exists an extension field E of f, and an element alpha belongs to E such that f of alpha equals 0. We have to prove for any polynomial, f non-constant polynomial in f of x, you can find there exists an extension field E of f, and an element alpha belongs to E such that f of alpha equal to 0. That non-constant polynomial must have a root in that extension field. This is the statement of Chronicles Theorem. Okay. Now before moving to the proof, we are using one result. Okay, now this is that result. Okay, let if f is a field, then every non-constant polynomial f of x belongs to f of x can be factored in f of x into product of irreducible polynomials. This is already discussed in your first sum. Okay, every non-constant polynomial f of x can be factored into product of irreducible polynomial, and these irreducible polynomials be unique except for order and for unit factors in f. Okay, so in order to prove f of x must have a root in E, it is enough to prove if p of x is an irreducible polynomial which is in the factorization of f of x, then it is enough to show that there exists an alpha belongs to E such that p of alpha equal to 0. I am repeating. By this theorem, f of x, our polynomial is f of x. Non-constant polynomial is f of x. By this theorem, this f of x can be factored into product of irreducible polynomial. Okay, and let P of x be an irreducible polynomial in such a factorization, and P of x be one of the polynomial in such a factorization. So it is sufficient to find an extension field E of f containing an element alpha such that P of alpha equal to 0. Okay, since P of x is an irreducible polynomial in f of x, by theorem 3.7, ideal generated by P of x is maximum. We have already discussed this theorem in our last class. If P of x is an irreducible polynomial, the ideal generated by P of x is a maximal ideal. Then this is a maximal ideal, then f of x over ideal generated by P of x is a field. Okay, so now what we are going to prove is, by this is a field, and we are going to prove f is isomorphic to a subfield of f of x over ideal generated by P of x. F of x over ideal generated by P of x is a field if we prove f is isomorphic to a subfield of f of x over ideal generated by P of x, then f must be a subfield of this one. That is, this is an extension field of f. Actually, here we are using isomorphically equivalent to. Okay, so our aim is to prove f is isomorphic to a subfield of f of x over ideal generated by P of x. Now, what about the elements in f of x over ideal generated? The elements of this set is of the form some g of x plus ideal generated by P of x, where g of x belongs to f of x. Okay. Now define a map psi from f to f of x over P of x by psi of a equal to a plus ideal generated by P of x. Here this is actually f of x over. Okay. Define a map psi from f to f of x over ideal generated by P of x by psi of a equal to a plus ideal generated by P of x for a belongs to f. Okay, now we are going to prove psi is 1 to 1. Psi of a equal to psi of b implies what we get? A plus ideal generated by equal to b plus ideal generated by P of x. We have a result a plus h equal to b plus h implies AB inverse belongs to H. We have this result. Using this result, A inverse means here addition, A minus B belongs to ideal generated by P of x. We have A plus N equal to B plus N implies A minus B belongs to N. We have that result. Okay, therefore, A minus B belongs to P of x. Now, A and B belongs to F implies AB belongs to F. Also, AB belongs to ideal generated by P of x. Ideal P of x is an irreducible polynomial, means P of x need not be a constant. Okay, so A minus B, they are constant, and that is belongs to ideal generated by P of x means A minus B must be equal to 0. Here P of x is a polynomial, means A minus B constant, and all elements of these ideals are multiples of P of x. Okay. So the only possibility is A minus B must be equal to 0. Therefore, A must be equal to B. Thus, we get psi of A equal to psi of B implies A equal to B. This implies psi is 1 to 1. Now, we are going to prove psi is a homomorphism. Let A comma B belongs to F. Psi of A plus B equal to this one, which is same as A plus ideal generated by P of x plus B plus ideal generated by P of x, which is equal to psi of A plus psi of B. Here, F of S are rings. Okay, so we have to consider ring homomorphism. Now psi of AB equal to A plus ideal AB plus ideal generated by P of x, which is same as A plus ideal generated by P of x into B plus ideal generated by P of x, which is equal to psi of A into psi of B. Thus we get psi of A plus B equal to psi of A plus psi of B, psi of AB equal to psi of A into psi of B. Hence psi is a homomorphism that maps F onto a subfield of f of x over ideal generated by P of x, because psi is a map from f to f of x over ideal generated by P of x. This is 1 to 1. Also, it is a homomorphism. Therefore, this is isomorphic to a subset of this field. Okay, subset of a field which is a subfield. Okay, that means psi is a homomorphism that maps F onto a subfield of. Here we are using the notation onto a subfield of f of x over ideal generated by p of x. Therefore, we can identify f with set of all a plus ideal generated by p of x. A belongs to f. Okay, by the means of the map psi. And if you take E as f of x over ideal generated by p of x, then clearly E is an extension field of f. We are identifying elements of f with a plus ideal generated by p of x for every a belongs to f. We are a mapped to a plus ideal generated by p. Then clearly this is a subfield of our E. So you have to remember one thing. If you have to find extension field, you have to find an extension field like this, ideal generated by p of x. This is the extension field. Now we have to prove one more thing. What we have to prove? Thus we find an extension field, and we have to prove one more thing, that is we have to find an element alpha belongs to E such that f of alpha equal to 0. Okay. For this you have to remember this theorem, evaluation homomorphism. There is no need to write this theorem in the proof of our theorem. This is just only for recalling this theorem. What is evaluation homomorphism? Let f be a subfield of a field E, and let alpha be an element of E, and let x be an indeterminate. Then the map phi alpha from f of x to E defined by phi alpha of a naught plus etc plus a n x raised to n equal to a naught plus a1 alpha plus etc plus a n alpha raised to n for a naught etc belongs to f of x is a homomorphism of f of x into E. Okay, what is the map actually? Polynomial x is replaced by alpha. So let us set alpha equal to x plus ideal generated by p of x. Then clearly alpha belongs to E because E is actually f of x over ideal generated by p of x. You take some x for element in f of x and this one. Therefore, clearly alpha belongs to E. Now consider the evaluation homomorphism phi alpha from f of x to E given by above theorem. Now let if p of x equal to this one, ai belongs to f. What is phi alpha of p of x? A naught plus a1 alpha plus etc plus alpha raised to n p alpha. Okay, and what we have to prove is we have to prove p of alpha equal to 0. Actually, we have to prove p of alpha equal to 0 in E. Now, what is p of alpha? P of alpha is a naught plus a1 for alpha x plus ideal generated by p of x a2. Okay, and we get this one. Ideal, this is actually p of x and which is equal to ideal. Therefore, p of alpha equal to 0 in f of x over ideal generated by p of x. Thus, we get an element alpha in E such that p of alpha equal to 0. Therefore, we get f of alpha equal to 0. This is a Chronicles theorem. Now, moving to one example. Let f equal to r and f of x equal to x square plus 1. We have to find an extension field of R. Okay, and an element alpha belongs to E such that f of alpha equal to 0. F of x equal to this one, you have to factorize this. Okay, clearly f of x has no zeros in R. Therefore, x square plus 1 is irreducible over R. Okay, so we cannot find. We know that this is x minus I into x plus I. Okay, but this is not possible because I not belongs to R. This is not a fact. We cannot factorize x square plus 1 in R. Therefore, this is an irreducible polynomial. Okay, so ideal generated by x square plus 1 is a maximal ideal. Therefore, R of x over ideal generated by x square plus 1 is a field. Okay, so this is our extension field. Now, we have to find an element such that our f of alpha equal to 0. So, identify R belongs to R with R plus, we have identified f with elements in f with a belongs to f with a plus ideal generated by p of s. In the same manner, R with r plus x square plus 1 in r of x over ideal generated by x square plus 1. We can view R as a subfield of this one. That is, E is an extension field of R. Now, if you take alpha equal to x plus x square plus 1, what is f of alpha? Alpha square plus 1. That is x plus x square plus 1 whole square plus 1. X square plus 2x x square plus 1 plus x square plus 1 whole square plus 1. That's equal to x square plus 1 plus ideal generated by x square plus 1, which is equal to, because x square plus 1 is clearly in ideal generated by x square plus, which is equal to ideal generated by x square plus 1, and which is equal to 0 in r of x over ideal generated by x square plus 1. That is, alpha is a 0 of x square plus 1. Okay, so what is our extension field? R of x over ideal generated by x square plus 1. Okay, in the last part we will prove this is isomorphic to C. Now let f equal to q and f of x equal to this one. Find an extension field E of f and an element alpha belongs to E such that f of alpha equal to 0. Here we have f of x is this one, and we can factorize f of x like this. Note that these both are irreducible over q. So consider x square minus 2, since this is maximal ideal. This is a irreducible, therefore ideal generated by x square minus 2 is maximal. Q of x over x square minus 2 is a field. Similarly, q of x over ideal generated by x square minus 3 is also a field. If you identify q with q plus ideal generated by x square minus 2 in this one, we can view q as a subfield of this one. That is, q is an extension field of q. Now let alpha equal to x plus x square minus 2, ideal generated by x square minus 2. F of alpha equal to this one. Substituting, expanding, we get x square minus 2, which is equal to 0 in q of x over ideal generated by x square minus 2. Thus we get f of alpha equal to 0, that is, alpha is a 0 of this one. Similarly, we are considering x square minus 3. Okay, no problem. Okay, same manner, finally we get f of alpha equal to 0. Therefore, if you have to find extension field of q for the polynomial x raised to 4 minus I x square plus 6, then extension field, you can take extension field either this as x square minus 2, or you can take q of x over ideal generated by x cube minus 3. Okay, that's all for today's class.